So today we're going to continue on learning about empirical and molecular formulas. Last time we met, we talked about percent composition, and so there is a review slide here if you wanted to take a look at that. It is slide 2 in the notes located in Canvas. We aren't going to go through all of this again today, so I'm going to assume that you know how to do percent composition. And we are going to talk about empirical formulas and molecular formulas. So first, we like to do definitions, and so molecular formula, remember, is just the actual formula. So these are the formulas that we've been working with all along. H2O is a molecular formula. NaCl is a molecular formula. Here, the example of glucose, C6H12O6. That's a molecular formula. If we look on the left here, empirical formula is defined as the lowest ratio of elements in a molecular formula. So if we go back to our glucose example, which is a 6 to 12 to 6 ratio, we can reduce that down to a 1 to 2 to 1 ratio. So the empirical formula for glucose would be C1H2O1. But we don't write the 1, so it would just be it would just be CH2O. So again, going from C6H12O6 down to CH2O. So empirical formulas are like, in math, when you reduce something, it's the lowest common denominator reduced down as far as you can. When we have this information, what this does is it provides us an opportunity to say, okay, I have this sample, and I know that my sample has a ratio of carbon to hydrogen to oxygen of 1 to 2 to 1. And so we can get an empirical formula just knowing that ratio of elements. So today I'm going to teach you how to get an empirical formula from a percentage or percent composition, and then how we can turn that empirical formula into a molecular formula once you have that information. So we're just going to start off with an example right away. These are the steps that we're going to use in this example. So either you're going to have to calculate a percent, or I'm going to give you a percent for each element in your formula. Once you have that percent, you then assume that your sample is 100 grams. So by doing that, we can just take our percentage and turn that into grams. So for example, if you have 40.05% sulfur, and our sample is 100 grams, that means we would have 40.05 grams of sulfur. Same with oxygen, okay? So we assume 100 grams, therefore our percents become our number of grams. The next step then is we would take those grams and convert to moles, and then lastly we would divide the moles by the lowest mole number. And I'm going to show you what that means because that's probably a little confusing. So let's take a look at our example here. I took my 40.05% sulfur and converted that to grams of sulfur. Same with the oxygen. 59.95 turned into grams. 59.95. Step 2, over here on the right, I converted my grams into moles. So in doing that, I look up sulfur on the periodic table, and I see that sulfur has a molar mass of 32.07. So I'm going to take the grams given, which is 40.05, and I'm going to multiply it by my conversion factor. And I know in 1 mole, there's 32.07 grams. I got this conversion factor from the periodic table. So to solve, I take 40.05 times 1 divided by 32.07. And that gives me an answer here typed in black. So 1.2488 moles of sulfur. Notice that I really drag out these decimals, and that's going to become super helpful later on. Significant figures here don't matter. And so drag this out, I would say, to 4 decimal places to make your calculations easier. If I go down to oxygen, I'm going to do the same thing. So 59.95 grams of oxygen. I use my conversion factor, and my periodic table tells me that 1 mole of oxygen is equal to 16 grams. So 59.95 times 1 divided by 16 gives me 3.7469 moles of oxygen. So quick recap. I took my percents, I just made it into grams. I took my grams and I converted it into moles. And now this pink part, this was that last step here on this previous slide. I'm going to divide all of my moles that I just calculated by the lowest number of moles. So my lowest is 1.2488, right? I just compare my mole numbers. So this is 1.2488, this is 3.7469, this one's lower. I'm going to divide both of these by my lowest mole number. And what that's going to do is that's going to give me an answer of 1. And then comparatively speaking, we'll see what the mole number would be for the other element. And in this case, I get 3. So I have 1 sulfur to every 3 oxygens. We can't keep it in these decimals because we can't have part of a mole or part of an atom in a formula. So we have to somehow get it into whole numbers. So by dividing by this lowest mole number, you're going to get whole numbers, or you'll get close to whole numbers, and I'll show you how to solve that in the next problem. So this means I have 1 sulfur for every 3 oxygens. So again, this is my empirical formula. So if my ratio is 1 sulfur to 3 oxygens, my empirical formula is 1 sulfur and 3 oxygens, or SO3. So if you guys need to pause and rewind and look back and all that stuff, do that now. And I am going to move on to the next example when you are ready. So now that we have our empirical formula, or our reduced formula, how do I get my original molecular formula from that? To do that, you're just dividing 2 numbers. You're going to take the molecular molar mass, so that's the mass of the original formula, divided by the empirical molar mass. Okay? So in the problem, I have to give you the molecular mass. So in this case, I'm telling you the molecular mass of our molecular formula is 160.1 grams per mole. To get my empirical formula mass, I need to add up SO3 from the periodic table. So 1 sulfur plus 3 oxygens gives me 80.06 grams per mole. So what this is telling you is that my molecule is twice as big as my empirical molecule. So take 160.1 divided by 80.6, and you get an answer of 2. That means my original molecular formula is 2 times the amount of my empirical formula. So if empirical is SO3, I'm going to multiply everything times 2, so I'll have 2 sulfurs and 6 oxygens, and that would be my molecular formula. And if you want to go back and check to make sure you did it right, add up 2 S's and 6 O's from the periodic table, and it should add up to the mass that was given to you, which is 160.1. Again, take a second and go back if you need to check anything, and then we'll go on to example number 2. Okay, so I'm going to challenge you guys to try this problem on your own. So I'm telling you aspirin has a molar mass of 180.2 grams. And I'm telling you that your sample has 60% carbon, 4.48% hydrogen, and 35.52% oxygen. So go through the steps that we just went through. If you need to rewind the video and look at the steps again, feel free to do that. But on a piece of paper, try this one on your own and pause it here, and then come back and see if you did it correctly. So I'm going to take my percents and convert to grams. So 60% means 60 grams. 4.48 is 4.48. 35.52 is 35.52. So I've got my grams of carbon, hydrogen, and oxygen. I'm going to divide by the molar mass on the periodic table. So carbon is 12.01. So 60 divided by 12.01 gives me 4.9958. Same with hydrogen. 4.48 divided by H on the periodic table is 1.01, and I get 4.4356. And the same thing with oxygen. Dividing by that molar mass, and I get 2.22. So of these three mole numbers, 2.22 is the lowest, the smallest. So I'm going to divide everything by 2.22 here in pink. And that gives me 2.25 carbons to 1.998, which that's, close enough to 2 that we can round that to 2, and then 1. So this 2.25 is not a whole number, and it's not close enough, it's not within several thousandths. So I need to figure out a way to get all of these pink numbers whole. So you ask yourself, what number could I multiply by to ensure that every one of them is a whole number? If I multiply, and this is kind of trial and error, if I multiply 2.25 times 4, I get 9. I get a whole number. So I'm going to multiply all three of them times 4. So this would give me 9, 2 times 4 is 8, and 1 times 4 is 4. So that means I have a 9 carbon to 8 hydrogen to 4 oxygen ratio. And so my empirical formula would be C9H8O4. If I add that mass up from the periodic table, I get 180 grams. So going back to my original question, I said the molar mass, or the mass of a molecule, so the whole molecular formula has a mass of 180.2 grams. So 180 divided by 180 is 1. So that means I'm going to multiply my empirical formula times 1, which means that the molecular formula times 1 is the same exact as the empirical formula. So C9H8O4. And that may happen sometimes. You can have an empirical and molecular formula be the same. It just means it couldn't be reduced. It was already reduced down as far as it could be. So here's one more example, and I just want to point something out. And again, I'm going to have you guys try it and then pause, pause first and then try it, and then I will show the answer up on the screen for you. The only difference with this one, it's telling you a compound has 85.7% carbon. The other element is hydrogen. And I don't give you a percent for that. So the question is, well, if you don't have a percent, how do you figure this out? Well, if 85.7% of it is carbon, 100 minus that, because remember, it has to equal 100%, right? So 100 minus that would be the amount of hydrogen in your compound, in your sample. So I also tell you that the molecular formula mass is 84 grams. So do all the steps that we just did and see if you can calculate this. So pause here and then come back on when you're done and look at the answer. So here's the answer. And why don't you pause the screen and compare it to what you wrote down and see if you got the same thing that I did. With an answer, empirical formula is CH2, your molecular formula is C6H12. So take a pause and make sure that you have the same formulas that I do. Okay, lastly, if you want some help, there's an extra link here on the empirical and molecular formula video. So remember, these notes are in your Canvas page. I just made this video to go along with it. So all of that is there for you if you just want to look through slides. But if you need to come back and listen to an explanation, feel free to always come back here and check out as well. I will talk to you soon.